On to the next example, and I'm going to say I don't want to open up another notepad, so I'm literally just going to click over here. I'm going to say File, Save As, and I'm going to make it example 2 and save. I already have it. Yeah, save over it. So now I have 2 duplicates of this, and this is technically example 2 now. And it's not the DC adapter, I believe. Oh gosh, is it the oscillator? Let's take a look. So I'm going to get rid of this. Let's move this over here. And here is the oscillator. You can see I already kind of wrote on it. Let's go ahead and clear this all out. There we go. All right. So for those of you who don't really want to watch the entire video, here was the example we just did. And then for part 2, here is the example we're going to do for the oscillator. And I might change up the node names in this video, but we'll see as it goes. And I'm going to try to make it as quick as I can. All right. So we take our picture, we say, okay, let's say, if you notice, this is a 5 volt. This is a 5 volt. We're going to just have one power supply that's going to give out 5 volts to both of those. And I'm going to go ahead, since this says VDD, I'm going to go ahead and name it VDD. And I'm going to name this, I'm going to say DD for the node. Same thing over here I'll do for VS. You could do a positive, you could make this a 5 volt power supply, 5 volt voltage supply, or you can make it like this and you could just do -5 volts. It doesn't matter, it just depends on how you reference it. So we're going to do that as well. So to get started, first thing I'm going to do is, it's not the DC adapter, it's going to be our oscillator. And for this one, I'm not going to use the MCP6004. I'm going to be using a different operational amplifier because we have lots of different ones. I'm going to be using the, what is it, the LM324? Double check. Yes, the LM324. I already have this circuit. You know, I like to dive into some of these. So let's go ahead and open it up and look at it. Ooh, so this one actually, it says sub-circuit, LM324. Sub-circuit, that means we're going to be using the X. We're going to be using X for the name when we call it. Also, if you notice, we have 1, 2, 3, 4, 5 here. That's because it takes in 5 nodes. It'll take, the first node will be the non-inverting input, which is the positive. Our inverting, negative. Positive power supply, negative power supply, positive, negative. And then we have our output for the operational amplifier, which is right here. And you can always open up, and if you download a good netlist for these circuits, it'll have this listed out here, kind of referencing what each node is listed for. I'm going to close this because I already know it, but definitely take a look, go back, pause it, check it out. All right, so we're not using a alternating current in this one. We're just using a direct current. Let's go ahead and clear this. We don't have V in, we're just going to be using VDD, and we're going to be using a VSS. So VDD, we're going to say, let's call it DD. We have a reference, we use 5 volts, and then we'll use SS, 0 and -5 volts. I'm going to get rid of the 5 or the volts because I don't even need them. Next thing I'm going to do is that I'm going to have these resistors here. So let's do R1, R2, we're going to do R1, and we're going to do from this node right here, we already have that. So we're going to call it DDD or DD, which is this guy. And then I'm going to call this node 1. Sure, let's do node 1, and we'll call this one node 2. Call this node 3. Call this node, let's call this node out, just so that we know it. Let's call this node 4 over here. And then this, I'm going to ignore the LED. I'm just going to be basically paying attention to this output, or this load resistor, or called R out. So let's do the resistor. It goes from our DD node and it goes down to node 1. And then we're going to do a resistor value of, let's do 15K. This one's going to go from 1 to 0, and this one's also going to be 15K. If you know anything about voltage dividers, this is just going to give us 2.5 volts, which is right, because both these are equal, it's going to split the voltage. And this is a buffer operational amplifier, which means that we're using a reference voltage and we're going to be producing that same voltage, but it's going to be basically more stable in the short term, I guess you could say that. Okay, so the operational amplifier. If you remember, it took in 5 inputs. We use the letter X for our subcircuit. I'm going to call it X1. Our first one is going to be the positive, so it's going to be 1. Negative input, it's going to be 2. We have our positive, which is power supply, DD, negative power splice, SS, and the output, which is also going to be 2 since the output and the negative are connected for our feedback. So we still need our name. So I'm going to say LM324. All right, so now we're going to have RX, 10, we got to go from 2 to 3, 10K, RF from 3 to out, which is going to be 10K. And we're going to have, let's go ahead and put the other op amp in there. Let's do X2. Positive is going to be 3, negative is going to be 4. We're going to have DD, SS for the power, and then it's going to actually go to out. And then LM324. So then next thing we're going to do, we have the op amp in here. If you notice I'm snaking around, it's always good to start from one spot and go around in a circle. Let's put in this resistor. Let's call it I'm going to call it R4 or R3. Let's say, I don't know what to make this one, R3, let's do 22K. Is that what I made last time? Oh, but I have to do the nodes. It's going to go from out to 4, because that's going to be for our negative feedback. And then we're going to do the capacitor, let's call it C1, and it's going to go from 4 to 0. And we're going to do 1 micro, or I think in this example we use 4.7 microfarads. I'm going to throw something at you guys for some. Here's something new. IC equals 0.1. What is that? What is that doing? IC, it either means initial conditions or it means initial charge, which means that our capacitor has an initial charge of 0.1 volts. That is at the moment we start running time, or at the moment the circuit starts, it'll have that voltage. I don't think it matters too much, but I'm going to put it there anyways, just to introduce it to people. Okay, so everything over here is wired up. Now we just need, I'm ignoring the LED, so we're just going to take from V out, we're just going to have this resistor here. So R out, and it's going to go from out to 0. And it's going to have, let's do 680 ohms. All right, and then we're going to still use .tran. I don't need this. We're going to do .tran, but we're going to use different time increments. Let's do every 0.1 millisecond, and let's run it for 1 second. Let's make it bigger. And let's hit run. All right, add traces. If you remember, our output is actually labeled as out, but I might want to put in, let's put the input. Oh, we don't have an input because this is, yeah, we don't. So we just want to see the output because we just have a constant voltage going in. Ooh, now we have a square wave. So this is our oscillator. And all we have is power supplies and resistors, capacitors, and op amps. All right. That was for this example. And again, I don't need that .op because when I hit run, it does fine without it. So Here, let me carry on. I'll show the next example, but let me close that. We're going to do our third example. So I'm going to do File, Save As. Let's do example 3. Yes, replace it. All right, so now we're doing example 3, which let's take a look at what example 3 is. Here's our solution already. I'm just going to do a Sallen key high pass filter. So this will be a really quick circuit. The reason I want to show this is because I'm going to be showing that how to use, instead of putting in like sine, you can actually just put AC and it'll do a full frequency sweep. It'll basically, it's used for our Bode plots. Another thing you can do is you can also call in a wave file and input into the system and then output it as a file as well. And I'll show you how to do that. All right, so let me open up our notepad. Scroll to the right, I have it right here. I'm actually going to reuse those nodes. Let's open up our LTspice. All right, example 3, Sallen key high pass filter. All right, for this guy, let's go ahead and remove all this. So let's do a VN, and we're going to say from 0 to 1. This will be right here, 0 to 1. And then I'm going to say AC 1. Okay, just making sure I didn't forget anything. AC, and it's going to be alternating just 1 volt. And then the next thing we're going to do is we're going to make our capacitor from 1 to 2, capacitor 2 from 2 to 3, a resistor named R1 from 2 to 4, and then from R2 from 3 to 0. And I did that pretty quick because I already had all labeled. From 1 to 2, 2 to 3, 3 to 0. This goes from 2, this resistor goes from 2 to 4, and 4 is connecting a bunch of stuff over here. Also, if you notice, this op amp doesn't actually have any power supplies. That's because in ideal cases, we can actually just use what I think is called the ideal op amp. That's an actual file I have. Let me open it. Let me make sure ideal op amp. I named it correctly. That looks good. Let's go ahead and open it. Look at it. I didn't create this. Someone else did. This is an ideal op amp. It's not, it's very simple because we don't even need the power supplies. It's treating it, as if it had all the power supply I needed. Non-inverting, inverting output. So it's almost the same syntax as the regular op amp that we were using, except we don't have the power supplies. So let's go ahead and label it the same, or put it in the same way it is. So X, let's call it X1, and we're going to do positive, which is 3 right here, negative, which is going to be 4, and then the output is also going to be 4. And then we're going to do, I need to double check the name. Ideal op amp, because if you notice, it's actually named different than the file name. It's named op amp. So op amp. All right, I need all the values for this. So C1, I already did the calculations for this. 200, was it 200 micro, right? 200 nanofarads. 200 nanofarads. 707.1, and then 1.414K or kilo ohms. So the reason why I use these values is because I designed this high pass Sallen key filter, and it will basically, I designed it to have a cutoff frequency at 800 hertz, which means all of our lower frequencies should be attenuated. Our cutoff frequency should be treated at -3 decibels at 800 hertz, hopefully. Now we actually don't use the dot tran anymore for this. When we do an AC sweep, we can do a dot, let's get space, dot AC, First number, okay. We could put in linear. This will be like a normal graph. You could do oct, which is going to be in eighths, which is it's logarithmic, but it's in eighths instead of 10, or in yeah. And then you could do decades, which is logarithmic by 10, which is what we like for Bode plots. The next thing is you need to put in how many samples we're doing. Let's do 100. And then we're also going to do the range, which is, let's do from 100 hertz to 10 kilohertz. That seems good enough. Let's run it. Add trace. Ooh, let's make it bigger. Run it. Add traces. Let's do the input, or no, we don't even need the input. We just need the output, which is 4. We have to remember that. If you don't label them out, then you should remember what node was your actual output. So this other line right here, I'll say that is actually the phase. This darker line is the actual magnitude. And if you notice, it's in decibels and it's in tenths, just like that's why it's in decades. So this is our Bode plot base. We're already there. Let's take a look to make sure we did this right. What you can do is you can actually hover up here. Instead of right-clicking to get the color, you can left-click, and now you have a cursor, and you can drag this. So -3 decibels, let's go about there. And you can see over here the magnitude and all the information. There's about -3, which is really close to 800. Close enough for my taste. And it'll give you the phase shift and everything else going on as well. So that's great. Now we designed a Sallen key high pass filter. This is only a second order filter. And I would have to show the math to really explain why it's second order. But that's great. We just simulate a circuit. We could actually use this. We can actually use it. We can, let's see if I remember how to do this. Or look it up. Okay, so let's get rid of this. I'm going to comment it out. We're still going to have the VN like we did normally from 0 to 1, except now instead of AC, what we're going to do is we're going to call, I'm going to use a wave file. Wave file equals, and let's do, I don't actually have a wave file in our folder. If you want to call a wave file, if you want to call any of these included files, it has to be in your folder. I'm just going to call it audio file name .wave, because that's what you need to put. You need to put the name of the file, what type of file it is, .wave. It'll say it in the name. And there you go. If you run it, it'll go through the circuit. However, I want to get this as a file. Like I want to actually run through the circuit, and as soon as it gets out, I want the result. So what I do now is I do .wave. Or it's a .wave with a E. And then I have to do, let's put out, this is the name of your file that's going to be put into your folder. So I'm going to put output audio file name .wave. And then now this next information, I'm going to put a 16 here. What this 16 is, and you can look it up. If you forget, you can go on Google and be like, hey, LTspice .wave files. So this 16 right here is basically kind of for digital to analog converter, or analog to digital, or basically it's saying that we're going to be using 16 bits. So it's pretty high precision. You could decrease it, really doesn't matter. But if you get low, you're not going to get as great of an audio file out. Next thing I'm going to do is I'm going to do 44.1K. That is samples per simulated second. So I don't think it needs to be 44.1K, but I'm just putting a larger number there. In one of the examples I have online that I found, I think they just used 10 or wait, 10K or 40K, or I can't remember. Another thing, the next thing is I'm going to put 12, or not 12. I'm going to put 4, because 4 is our output. That's what we're actually taking from. After this information, you can put in 4, you can put in node 3, 2, 1, and it will save all of the stuff that's going on with those nodes into that audio or that .wave file. I only need one of the nodes, so I'm only putting down one of the nodes. Okay, so that's it. If you hit run, your WAV file will go through, make sure it's in the right folder. And the output file, which it's going to be named whatever you put right here, and it will be put into the folder. And this is just information. Oh, let's do one more thing. Dot options. Dot option. There's certain things in LTspice that you can change that are default cases. I went ahead and I looked it up and I opened up options that you can do in your simulator for LTspice. I just Googled it. I'm not an expert on any of these, but you can see that a lot of these have, this column right here is default values. And that's all I really care about is the default value and the description of what's going on. So what I want to do, I want to use this one. This one's num digit, which basically if you read into it, it's default 6. And it says that if num digit is set higher than 6, double precision is used for dependent variable data. So I want that. So I'm going to say num digit equals 7. It's greater than 6, meaning it's double the precision that's going on. Let's go back into our options. Let's look around. The next thing I want is I want plot win size. It says number of data points to compress in one window set to 0 to disable compression. I want to disable the compression. So let's do plot win size equals 0. That's just extras. If you don't know what it does, don't worry about it too much. But if you want to change more things in your LTspice simulation, you can always look up options and certain things in here. Conductance added to every PN junction to aid conversions, flags, external current sources as loads, things like that, delay. These are just things that already have default cases in the simulation that you can change. But yeah. All right. I am going to go into our last example. I'm going to try to go over it fairly quickly. This video is already getting too long. Here's our last example. Pretty small, short, sweet. It's not anything complicated, only a few lines of code. The reason I wanted to go over this example is because instead of the .ac sweep, this is a .dc sweep. And this is nice so that we can do characteristic function or characteristic graphs, tables, or whatever. So here, let's open up this guy first. Here it is right here. Oh, that's not it actually. Let's go ahead and steal the picture. All right, so open up LTspice. Let's get rid of that. Let's go over here. File, save as, because we need, this is gonna be our 4th example. Replace it. Example 4. This is a NPN BJT common emitter amplifier. And in this case, we're going to be using the 2N, what is it? 39, what is it? I can't remember. 2N3904. Let's go ahead and open it up to look at it. Ooh, this one's pretty small. And I took some notes. 2N3904.cir. That's the file name. And if you notice, it's not a whole lot going on. There is some stuff that I don't understand, but it has a basic. And when you call it, I believe you call it as Q, or I think you can call it anything else, but I call it as Q. The first node is going to be our collector, which is this guy. Second node is going to be the base, which is this guy. Third node is going to be the emitter. And then you have to have the name. So let's go ahead and do that. Let's go ahead. We don't really need any of that. So VN, I'm going to do from 1, 0. Positive is going to be the 1, which we already have there. I want to do a DC sweep, so I'm going to do DC. I don't have the example that I made. Oh yeah, I do actually. It's right DC 0. I'm going to say 0 volt. Or wait, no, that's not how you do it. 1, 0, and then I'm going to say 0 volts to start with. We're going to do RB. It's going to go from 1 to 2. And I'm going to do like 51K. I'm going to do RC. It's going to go from 3 to 4. And I'm going to do 1K. Yeah. And then the transistor, Q1. That's the name of the transistor, is Q1. The collector is the first node. So it's going to be 4. Base is the next node, 2. Emitter is the third node, 0. And then we have to call its name, which is 2N3904. And yeah, so this is fine. If I run it, it'd be fine, but we want to do our DC sweep for our characteristic function. So I could do a dot DC. Then you need to do the name of the independent variable source you're sweeping, so VN. And then now you need to do from the start to stop, so 0 to 5, and then you need increments, so 0.01 volts each. So it'll go from 0 to 5 and increments of 0.01. Make it bigger. Let's run it. Add traces. So if you already notice, our domain is actually our input voltage. So we don't even really need to worry about that. So we want to look at our output, V out, which is node 4. Ooh, I did something wrong. 1, 0, VB. Oh, we forgot to power this thing. We forgot VCC. So I'm going to go ahead, let's put it right here. VCC, let's make it go from 3, 0, and it's going to be, what, 5 volts? Is that correct? VCC, it doesn't matter. Let's say 5 volts. Now let's run it. Yeah. Okay, so that is actually true. What it's going on is our input, we are sweeping it. So we start from 0. 0 volts is our input, and our output is going to be high. And then we have a transition. And then if we give basically higher voltages for our input, then our output's 0. What does that remind you of? That is a NOT gate. If our input is low, because it's from 0-ish area, if our input's low, our output's high. But if our output, or if our input is high, then our output is low. Okay, I think that's mostly it for this video. You can always click on this and get multiple cursors. You can have 2. And then if you notice here, it'll actually subtract them right here. If it's negative and it shouldn't be, then just flip the polarity. But I think that's it for this video. If there's anything I didn't cover, you're welcome to email me. I don't know everything, but I can certainly try to learn it or teach it. But thank you for watching, and I hope this helped.